Hello. In the previous video, we studied the natural logarithmic function, differentiation, definition of such function, and the number e. We know how to apply rules or properties of such function to find derivative. Today, we'll study integration. But before that, let's recall two formulas on differentiation. The derivative of ln of absolute of x with respect to the x is equal to 1 over x. And the derivative of ln of some function u is just u prime over u. It's the chain rule, right? The chain rule in here. From here, as we know from calculus 1, if you apply integration, right? So you have the following. Antiderivative of dx over x is equal to ln of absolute of x plus c. And from here, we have antiderivative of u prime dx over u equal to ln of absolute of u, right? Plus constant. But what is this? This substitution, right? So this is nothing but du over u equal to ln of absolute of u plus c. These are two formulas of integration involving logarithmic function. Okay, let's consider the following example. We need to find antiderivative of 2 over x. So 2 is a constant. We can take this out, right? We have 2 times dx over x, which is 2 ln absolute of x plus c. Okay? But, sometimes if you don't want to see the absolute in here, you can write that is nothing but ln of absolute of x squared. Because, you can bring any constant, right, to the power. I hope you remember that. Plus c, and this is nothing but ln of x squared plus c. But again, right, if you have x squared, right, and you want to take 2 out, don't forget that we need to apply absolute. So that is the thing, right? We need to pay attention. Of course, when x is bigger than 0, that's okay. When x is bigger than 0, you always have ln of x squared equal to ln of absolute of x, and that is ln of x. Okay, but in general, you need to have absolute. All right, let's consider another example. Now we have dx over 4x minus 1. So you can see, yeah, in the problem you don't have x, but you have, 4x minus 1. So probably we need to use substitution in this case, right? So if we are very careful, we may do in the following way. I may put u equal to 4x minus 1 because we want to do substitution, right? And from here I have du is equal to 4 dx, or dx is du over 4. When we do substitution, we need to rewrite our integral in terms of new variable. Okay, let me write it down so that we will not forget. When we do substitution, we need to just rewrite the original integral in terms of new variable. Okay, don't forget that. So once you already put u equal to 4x minus 1 right here, you need to rewrite everything. You need to express everything in terms of u. So that's why, once I took the derivative differential in this case, I need to solve for dx, right? So right now I have all information. I need to rewrite this integral in terms of u. I write this is equal to dx is du over 2. I have du over 4, sorry. And for x minus 1 is just u, you see. And since 1/4 is constant, I can write just 1/4 right here. And then that is du over u. We can use the second formula right here. Right? And then from here, I will get this is just 1/4 absolute of u plus c. And at this step, I need to plug, the substitution back here, right? Back here. So I will get 1/4 ln of absolute of 4x minus 1 plus c. Done. That is the answer. Now let's solve the following area problem. They give us some function y equal to x over x squared plus 1. And they ask us to find the area of the region bounded by the graph of this function, the x-axis, and the line x equal to 3. So this is the line x equal to 3. Okay. The x-axis is right here. And the graph like this. Of course, in this case, right, they give you the graph, so you don't have to graph the function. But, if they don't give you anything, so you need to graph the function to make sure that the graph is above or under the x-axis. I hope you still remember that problem, because sometimes the graph look like this. And this is the x-axis, right? And for such graph, you need to find the area of two regions in here. The area of this region is positive area. But the area of this guy is negative because the graph is under the x-axis. Does that make sense? So you have to find, two different areas in here and then take the difference. Don't forget that. So that's why, each time when you need to find the area of some region bounded by the graph of some function, you need to graph the function. Okay? But again, right, in this situation, we have very good function. What does mean good function? In this case, I know x. On the top, you have x. In the bottom, you have x squared plus 1, right? X squared plus 1 is always positive, right? Which is good. You see? And when x equal to 0, you see, when x equal to 0, the function is 0. You see that? And when x bigger than 0, so the function is always positive. Because x squared plus 1 is already positive. So when x is positive, the function is positive. That means the graph of the function is always above the x-axis. Does that make sense? So I can write explanation in here, right? So we have x squared plus 1 is always positive. Then for x between 0 and 3, x squared, no, not x squared, but x only over x squared plus 1 is always greater than or equal to 0. Okay, that means the graphs of the function, the graph of the function is above the x-axis, which is good because we know for such graph, in order to evaluate the area of the region, we just need to evaluate the definite integral. And we know exactly, based on this observation, the graph of this function has only one intersection with the x-axis. That is x equal to 0. We don't have another intersection, right? So even I don't know the exact graph of this function, but I know exactly the graph should look like this. Does that make sense? Maybe not concave, maybe not convex, right? I don't know. And sometimes in this situation, I don't care. I just care about if the graph is above axis on the whole interval or not. That's it. All right? Okay. Now I can find the area that is just definite integral from 0 to 3. Okay, the function right here, x over x squared plus 1 dx. Alright, let me write in this form. 03 x dx over x squared plus 1. So I hope you still remember the case, right? When you have combinations x dx and x squared, right? So in Calculus 1, we learn like x to the n dx and x to n plus 1 plus some number a, let's say that. So, you know, when you have something like that in your integral, you might think about substitution, because when you put u equal to this part and you differentiate u, you get just n plus 1 and then times x to the n dx. Okay, so you know we have to pay attention on this and on this. We have that situation right here. We have x dx and x squared plus 1. So I do substitution. I put u equal to x squared plus 1. And then from here I get du equal to 2x dx. You see? Or I write x dx is equal to du over 2. Because we need to express the original integral in terms of u. Don't forget that. Alright, now, you know, you might choose to change the integration limits 0 and 3. Because you already do substitution. Or you may just need to find antiderivative of the original function right here. At the end, you plug 0 and 3 into the formula. Whatever you want, okay? But I choose the second way. I will find the antiderivative of x over x squared plus 1. At the end, I plug 0 and 3 into that. Okay, so I will write antiderivative of x dx over x squared plus 1. This is just equal to antiderivative of du over 2, right? Because that is x dx. And x squared plus 1 is already u, so I have that form, which is 1 over 2 du over u. And we know this is ln of absolute of u plus c. Okay. Now I plug the substitution in here. I got 1 over 2 ln of absolute of x squared plus 1 plus c. So that is my antiderivative. Now I want to find the definite integral. No problem. I plug 0 and 3 into the antiderivative. I get that is 1 over 2 ln of what? 3 squared plus 1 and then minus ln of 0 plus 1, right? And in here I have 1/2 ln of 10. Here I have ln of 1. Okay, but what is ln of 1? Ln of 1 is 0. Okay, so from here I get 1 over 2 ln of 10, or approximately equal to 1.151. Okay, so you know that's how we can solve such problem. But why ln of 1 is 0? Do you remember that? Let me remind that. Because we have ln of x is integral from 1 to x dx over x. So, no, dt over t, sorry. dt over t. So when x equal to 1, right? You know, you evaluate integral from 1 to 1. That means you got 0. Is it? Okay. So, again, right? When you have such integral, you might choose two approaches. The first approach, you find antiderivative, as I do in here, and then plug 0 and 3 at the end. Or, after this substitution, you might change the integration limits right away. Whatever you want. Okay? In the following example, sometimes we need to change the function. not change the function. Sometimes we need to do a little bit with the function, okay, before we evaluate the integral. So we have x squared plus x plus 1 over x squared plus x plus 1. On the top you have square, right? In the bottom you also have square. So we think like we may simplify the function a little bit before integrate. So I will do in the following way. Of course, in the textbook they tell you, yeah, using long division before integrating, but for such function we don't need to use long division, because I see in here I have x squared plus 1, in here I have x squared and plus 1. So basically I just need to break the function into two functions. So I write integral of x squared plus 1 plus x, right? In here x squared plus 1 dx. And that is what? That is integral of x squared plus 1 over x squared plus 1 dx plus integral of x dx over x squared plus 1. You see, we already have this, right? This is just 1. So in the first integral I have antiderivative of dx. The second one is, we just did this recently, x dx over x squared plus 1, right? So for the first one I have, that is just x. For the second one we have combination x dx and then x squared plus 1. I will not solve this in detail. I just write the answer. So I write here just 1/2, okay, 2x dx and then x squared plus 1. The region I write 2 in here because derivative of x squared is 2x, right? So this is equal to x plus 1 over 2 ln of x squared plus 1 plus constant. Okay, it's just very short, and I think the function is not very difficult. But in case if you have something like x cubed plus x plus 1 over x squared plus x, so you may need to do long division, right? Let's consider the following example. Find the indefinite integral 2x dx over x plus 1 x squared. So yeah, we see x plus 1 x squared in here in the denominator, so we may think about log, right? But again, before that we need to do substitution. So I would do the following way. I put u equal to x plus 1, right? And once you put u equal to plus x plus 1, you need to solve everything in terms of u, right? I have du equal to dx. That is the first thing. But if you look at the original integral, you see x in here, right? So we still need to express x in terms of u. I will have another one. X is equal to u minus 1. You see that? Now we have all information to rewrite the original integral in terms of u. So let me denote this by I, which is like integral. So I have I equal to integral to x is u minus 1, dx is du, and then I have u squared. All right. I think we saw such. I'm sorry, here we should not have dx. We should have du. I remember in Calc 1, when we study integration, we solve such problem. So I have like 2 in here, and then again I break, right? I break u minus 1, over u squared into two functions. So I got u over u squared du, right? And minus du over u squared. Okay. From the first one, I get 2 times du over u minus 2 times in here. So u squared I rewrite as u to negative 2 du, because we want to use the power rule, right? And for this term, we use logarithmic function. You know, the power in this case just 1, right? We discussed about that in very first lecture. So I have 2 ln of absolute u minus 2. If I use the power rule, I got u to negative 2 plus 1 over negative 2 plus 1 plus constant. And then I plug the substitution back here because u is equal to x plus 1. I will get 2 times ln of absolute x plus 1 minus, so I might simplify this. Negative 2 plus 1 is negative 1, right? Negative 1 with negative 2 is just 2. So I write in here plus. Let me plus in here. Let me erase this. And then 2 times u to negative 1. So I got 1 over u, which is 1 over x plus 1 plus c. And that is the final answer. In order to finish today's video, I would like to solve some integrals involving trig functions. We know how to find antiderivative of sine, cosine. That's what we did in Calculus 1, but I think we never did with tangent and cotangent. We know about substitution, but you know, at that time we don't know the formula of antiderivative of 1 over x. Right, we just did that in this course. We use logarithmic function. Okay, so now for this function we can rewrite as, you know, sine of x dx over cosine of x. And since we have cosine in the denominator, we put u equal to cosine. Okay, so I write in here, put u equal to cosine of x and du equal to negative sine of x dx. Now I can rewrite my integral I, the original one, in terms of u. So I have u, the I equal to, we have sine x dx with the negative side, so I can bring negative 2 to the side of, you know, du. So I have negative du in here, okay? In here I have negative u over u, which is cosine, right here. So we know the formula already. That is negative ln of absolute of u, right, plus constant. And then we plug the substitution into this formula. We get negative ln of absolute of cosine of x plus c. Okay, so you see, it's pretty easy, right? If you solve antiderivative of cotangent of x dx, it's almost the same. Because cotangent is what? Is sine of x, is cosine of x over sine. Okay? Is cosine of x over sine. And for this integral, you put u equal to sine. You do almost the same thing. Okay? And you get what you need. Agree? So I've left that exercise for you. And, you know, we have some elementary trig functions like sine, cosine, tangent, cotangent, sequence, cosequence. We will not show you how to find antiderivative of such function, because, you know, it takes time, and I think the solution is not very natural. So I just copy formulas right here, and then please you need to make a formula sheet for yourself. Okay. All right, they are here. So if you need to evaluate sequence, antiderivative of sequence, so you have ln of sequence plus tangent. If you cosequence, you have right here, and so you have this formula. Okay, and in case if you replace the x with the u, right, with some function, so these formulas also work. All right, now let's apply what we already solved right here to find the average value of the function tangent on the interval 0, pi over 4. Before that, I would like to remind you the formula of the average value. So we have AV of the function is equal to 1 over b minus a, integral from a to b, f of x dx. Okay, so what is that? The meaning of the average value of function on some interval is, slide, you have some interval right here, a and b, and the definite integral, let's say that is, the area of this region, right? So the formula says, yeah, there exists some point here, so that you have a rectangle, and this rectangle has the same area with our region. And what is rectangle in this case, right? The area of rectangle equal to product of two sides. One side is b minus a. Okay. Another side is, let's say this is the point c star. So I have f of x of c star right here. Okay. So we have, b minus a times f of c star equal to definite integral from a to b, f of x dx. From here I get f of c star equal to 1 of b minus a to b, f of x dx. So that is called the average value of the function. Does that make sense? Basically what is that? That is the function value at the point c right here, such that, you have this identity. Okay. All right. So once we already have formula, I just plug number into this formula. I get pi over 4 minus 0, integral from 0 to pi over 4 tangent x dx. Okay. So we know antiderivative of tangent. So I just simplify this 1 over pi over 4. The derivative of tangent is what? Is negative ln of absolute of cosine of x, right? And this is evaluated from 0 to pi over 4. That's it. So I plug pi over 4 and 0 into this function. I get 1 over pi over 4 negative, let's say negative 1, right? And have ln of cosine of pi over 4 absolute minus ln of absolute cosine of 0. Okay, so you have negative, let's say 4 over pi. Okay, I just take the inverse, and cosine of pi over 4 is square root of 2 over 2. Cosine of 0 is 1, so ln of 1 is 0. Overall, I get ln of what? ln of square root of 2 over 2. And this is approximately equal to 0.441. Okay, so I hope that you enjoyed the video, and actually we have a couple problems in here, with trig functions and then with fractional functions. But again, right, basically, for such examples, we need to do substitution all the time. And sometimes if you see the form du over u, so that means we need to use the natural logarithmic function. That's it. So I think that is the only difference between this integration and the integration we did in Calculus 1. All right. So if you have any questions, please feel free to let me know. Okay. Thank you.